Good. And let's take a look at the book. Well, we're behind here. I need to go quicker here in this material. Hopefully, let's see here. Okay. Let's take a look at the book. We're in this chapter right here. The next chapter is going to be impulse and momentum. And let's take a look what we covered so far from chapter 6. Momentum, linear momentum. And the other rotational kinetics, okay, kinematics. Rotational kinematics. Okay. Rotational kinematics and dynamics. Kinematics and dynamics. More students coming. And let's take a look at our notes. Okay, so that's what we have done so far. We're doing conservative versus non-conservative forces. What I was doing some examples of conservative and non-conservative forces. I start with an example of non-conservative forces, so you can see in a mathematical sense, what does it mean to be a non-conservative force? And there's a reason why we do that, okay? There's a reason why we do that. We finished for a non-conservative force, and we are going to do a conservative force. An example of conservative force, okay? And I'm going to copy and paste in the next page. Okay. Today is the 6th of November. Right here. Let's take a look at my drawings and my PowerPoint slide. Okay, and here you go. That's a conservative force. What you have to remember. Let's see. Yeah, here you go. That's the one I want. That's the one I want. And view, grid lines. Example of conservative forces. Okay, so for conservative forces, you have no choice but to memorize what the conservative forces are. There are very few of them. Okay, let's write down here at the top. There are very few conservative forces. Most of them are non-conservative. So just memorize. So for the sake of this course, memorize the following conservative forces. Okay. The weight. And don't forget, there are two weights, right? The simplest weight is the mg. And I'm going to number them. Mg, okay, is the weight. This weight is the force of gravity nearby the Earth's surface. Not just the Earth, okay, and any other planet and any other planet's Earth and any other planet's surface. Okay, so we have the other weight that we saw, the weight from universal gravitation. This is also a conservative force. This weight, here go. I'm gonna write down here the equation for the weight taken from universal gravitation. I'm not gonna do, let's do it. I'm gonna do like as vectorial wise. Minus G, big M is small m, divided by R squared. And we have, just to simplify the notation, we're gonna write like this way. This weight, there's a distinction, very important distinction between this weight and the other one. This weight, this equation for the weight applies to any masses, applies to masses at any distance from the, apply to masses m at any distance from mass big M and vice versa. More students coming. Vice versa. Okay. The other weight, the other conservative force is not the weight. The other conservative force, the elastic force. The elastic force is given, and here I'm going to write down as well weight F equal to mg, like that. The elastic force. The elastic force is going to be given by it's going to be a minus here, a k here, and a vector position from the equilibrium position, from the position of equilibrium. And now we are going to do an example of conservative force for this one specifically. If you repeat that for the other two forces, you're going to get exactly the same thing, okay? And here you go. Here's the vertical direction. Here's the horizontal direction, and I'm moving a mass. Oh, this is a non-conservative force. Hang in there. This is a non-conservative force. Let's see here. I'll have to do that from scratch for a conservative force, unfortunately. Okay, anyway, I'll be able to reuse some of that of the conservative force. Okay, so here you go. This one here. Example of conservative force. And I'm going to do like that. From everything from scratch, right? Everything from scratch. I'm gonna erase that, and erase that. Start with the x-axis. I'm gonna prove to you that if whatever path you take, the work done by this specific conservative force is going to be the same. Okay, so here you go, x-axis, y-axis, step by step. And then we start with a mass. We start with a mass at point A. Okay, that's mass at point A. I'm gonna put mass lowercase m. And I want to move my mass from point A to point C, just like I did with the other one, right? If you remember that. So here you go, I'm gonna move this mass from point A to point B, and then from point B to point C. I'm gonna put it here, and let's not forget, while we move this mass, while I'm moving this mass, there is also a conservative force acting on this mass. This conservative force is the mg force. Let's say, I'm gonna put it midway here. Until it gets to point, here you go, mass m. And this is going to be mg. Okay. I'm gonna put it dashed here, so you know that it was initially at that position, right? Like that, better, right? And then we do the same for the next step. This mass is being moved. Let's not forget that was the mass was along the way. It was right here. I'm not gonna keep on making this, putting m in there. And then we have this other displacement from B to C. And here is the point C. And here is the same mass. I'm going to move it to this position. Okay, this one, I'm gonna put it at the position B here. And what I'm going to do, I'm going to calculate the work done by the weight mg along this path. I'm going along this path. And then I'm going to repeat the same thing for a different path. Okay, that's I'm going to call path number 1. Okay, so here we go. More students coming. We do not have the force of friction here. We have instead, we have the mg here, right? Oh. We also have oops. Mg here as well. This distance is A, this distance is B. We don't have this one here, because it's not the force of friction. Example of conservative force. And then we're going to repeat the same thing through a different path. Right? And then I'm going to do, all I have to do here is just to copy what I have here. Yep. Let's copy everything. X-axis, Y-axis, initial point A. Okay, but now this mass is moving initially, along the x-axis, right in here. And I'm going to put it as green. A, B, C. So I'm going to call here this point D. And this mass, that's midway, right? Let's put all the way down here. I don't have this one anymore. I don't have this one anymore. I don't have this one anymore. That's going to be distance B, just like we had before. And in the next step, like that. Bring it to the top, right? I call point D because it's a different point, right? Not the same one. I'm going to get rid of this so you can have a better look. What am I missing here? I'm missing this one here. And it goes to the same point C that we had before. We have A, B, C. Now we have A, D, C, right? We have two different paths. Oh, you go bring to the front. Now I can bring this guy back here. Sometimes PowerPoint are tricky. Like that. Point C, I'm gonna put the capital point C. Two different paths. And I'm gonna call that path 2. Go, path 2. Example of conservative force. Two different paths that takes to the same point. Okay. Let's review that again. And I'm gonna do the math. I shouldn't do the math. I just illustrated how we take the masses from one point to another through different paths. I did the simplest possible, but the simple possible path, but you can do that the most generic path as well, and you're gonna get the same result. Okay, so here you go. X axis, Y axis, the mass at point A is gonna move through a path 1, first upwards, the vertical, distance A, okay, and then along the horizontal, from A to B, from B to C. I call that path 1. This distance is A, and the other distance, okay, the other. Okay, and the other distance, I'm gonna do like that. A is going to be this one here. Okay. And this distance here, I'll call B. Yeah, okay, I already have B there. Here you go, B right in here. I'll take this one down here. And then we have this other pass. Okay? Just repeating what I did. You know, A through D to D, from D to C. Same distances. Okay, and B is this distance here. I'll put that in green. Okay. You know, all you have to do now is to calculate the work done by this force, by the weight, through the two different paths, okay? So the idea here is the following. Path 1, we want to know the work Yeah. The work from A to C is going to be the work from A to B. Oh. Plus the work from B to C. And don't forget the work of the weight. And then you repeat for pass number 2 is going to be different from A to C, yeah? And I'm gonna put a prime here because it's a different pass. Okay, pass 2 is gonna be the work from A to D, from D to C. Here I have to put a different notation to distinguish the two different paths, right? But here I don't have to do that because this subscript here is different from the subscript here. So let's do that one by one. The work done from A to B this one right in here. Work done from A to B. Notice that the displacement is upward and the force is downwards. So what does it mean? And I'm gonna put this coordinate here, A, in the other ones as well. Right? Because the force is contrary to the displacement vector, we are going to have that the work from A to B is going to be minus mg times A. Okay, and now we have to do this one here. Have to do the work from B to C. Going back. Okay, note that the displacement is perpendicular to the force. Consequently, the work from B to C is going to be equal to 0. And then we're going to repeat that for those other two. And oh, before we do that, let's get the network from A to C, right? The network from A to C is going to be minus MGA. Forget, because from B to C, this term here is going to be 0. Oops, don't do that. Here you go. And then we're going to do the same for A to D and from D to C. Going back to always refer to the drawings, right? Always refer to the drawings. And in order to make it look nicer and consistent too, I'm gonna make all those displacement vectors here the same colors as we had before. All right, this one is gonna be green, this one is gonna be green. Wait a minute. Yeah, that's okay. We're gonna do that. Green, green, and green. To make it consistent with the colors that we have for the second pass. There you go. This one's gonna be green as well. Okay. We're looking at this one from A to D. A to D. Displacement is perpendicular to the force. Consequently, the work done from A to D is 0. And now the displacement from D to C, the force is against the displacement. So look what we get. We get the same thing as we got for the other pass, MGA. Okay. So the work done from A to C through the second pass is going to be minus MGA. In other words, the work done from A to C along the first pass is equal to the work done from A to C along the second pass. Okay, so that's how we define conservative forces. That's how we define, that is how we define a conservative force. If you can, a conservative force, okay? And there's a reason why we do that. There's a reason why we do that. Okay, now remember, did you talk about kinetic energy already? We already talked about kinetic energy, right? Kinetic energy, we talked right here. Work kinetic energy theorem. Recall, consequently, the force F equal to mg is a conservative force. You repeat that for the law of universal gravitation, and the elastic force, and you get the same thing. And the nice thing is that it doesn't matter what path we take. Right now, I took a very simple path, but if I come up with a far more involved path, far more difficult path, full of wiggles and turns and twists, you still get the same thing, okay? You still get the same thing. Why do we define conservative and non-conservative forces? There's a reason. We do that because there is another type of energy that we call potential energy. Potential energy. Okay. And potential energy is applied, only to conservative forces. Okay, that's why we talk about conservative forces, because there is this other type of energy, in addition to kinetic energy, that is important in physics. Okay, so if kinetic, very important to remember, if kinetic energy is energy due to motion, okay, comma, potential energy is energy due to position. See the difference here? I can, instead of due to motion, let's write it down, due to velocity. Okay, that's the difference of those two types of energy. One depends on the velocity, the other depends on the position. And how do we define potential energy? How do we define potential energy, right? Potential energy. Let's take a look at the book. I want to take a look at the book, see this one right here, okay? Other forms of energy. Work done by variable force. Let's see here. See here, and C for non-conservative force, work done by non-conservative force. Let's see, what does he have it here? Here you go, potential energy. He's using P, conservation of mechanical energy, okay? So how is potential energy defined? Okay. You already saw that kinetic energy is defined as half mv squared. Okay. However, potential energy is defined in a different way. Potential energy is defined as being minus the work done by a conservative force. There is a reason why we put here, okay? The minus. Basically, we put the minus here to differentiate potential energy from the work done by a conservative force. That's all. That's the reason. This definition is very important. And now that we have this definition of potential energy, you're going to see something important in physics. That's called the conservation of energy, conservation of mechanical energy. Okay? It follows from the work kinetic energy theorem, the one that we derived before. Remember that? Let's go back. Before the exam, right? Before the exam, I came up with this result here. Let's say I came up with this result here. Remember? Work kinetic energy theorem. I'm going back to the work kinetic energy theorem. The work done by the net force is the final kinetic energy minus the initial kinetic energy. I'm going to delete this guy here. But we can also here write the work of the net force as being work of the net force is equal to the work of a conservative force plus the work of a non-conservative force. Okay, work of the net force is going to be the work of a conservative force plus the non-conservative force. This term here can be here written like that, and I'm going to simplify the notation now, so you don't keep on carrying too much stuff. You know, this thing can be here written as being work done by a conservative force plus the work done by a non-conservative force. And instead of writing down as work of the net force, I'm just going to simplify the notation as well. I'm going to write down as being the work of the net. It's subintended that's work of the net force. Okay? So everything follows from this simple theorem that you see here. Don't forget, work kinetic energy theorem is a theorem that applies to the net force only, to the work of the net force only. And we can have work done by conservative force and work done by non-conservative forces. I'm going to go even, I'm going to even simplify even further. Instead of con S, right? I'm going to put just C for conservative force, and C for non-conservative, and C for conservative. Okay. Special case. What's the special case? Work of non-conservative forces equal to 0. We see that with oftentimes we see something like that. Work done by non-conservative force is equal to 0. So now that we have this special case, I can rewrite my equation as being work of the conservative force is going to be equal to the difference in kinetic energy. Final kinetic energy minus initial kinetic energy. Okay. And let's not forget okay, so here you go. And the work done by a conservative force can also be written in terms of a final potential energy. Here you go. And don't forget that we have a negative sign here, right? Minus initial potential energy. Like that. And now we are going to have something very interesting. We're going to get, final potential energy is going to sum up with the initial potential energy. And then what do we get? We get what we call the law of conservation of mechanical energy. Okay, here you go. That's gonna get it. Okay. This summation here, kinetic plus potential energy, we call mechanical energy. This guy on the left, we call initial mechanical energy. And the guy on the right side, we call final mechanical energy. Okay? I will erase like that. Here you go. So potential and conservative forces conserve the energy, whereas non-conservative forces do not conserve the net energy, okay? So conservative forces are called conservative because they conserve the net energy. And conserve, by the way, conserve here. The conservation term here, what does it mean? The conservation term here has a different meaning in physics. Conservation means what you have at the beginning is equal to what you have at the end. Okay, that's what conservation means in physics in this context here. Okay, initial mechanical energy is equal to final mechanical energy. When something like that happens, we say that mechanical energy is conserved. And now that we have a situation like that, we can start solving some problems. What you see right in here, is genetic for any potential energy. But let's take a look at, and by the way, what you have here as well, should be not just potential energy is equal to minus WC, is difference in potential energy, okay? final potential energy minus initial potential energy is equal to minus the work done of the conservative force. Now let's do some examples, okay? Examples. The easiest of all examples, the easiest examples of potential energy, The easiest one is F equal to mg. That's the easiest one. Okay. So we are going to go ahead and we're going to come up with a. Now you know that no matter what the path you take, right, to go from one place to another, the potential energy is going to be the same. Now you know that. And let's see, I'm gonna get this one right in here. Okay. And now I'm gonna do it in a very generic way. Instead of calling A, I'm gonna call here this position, the position Y. There's a reason for that. And I have this path from A to C. That's gonna be a very generic path. All right. Oops, I don't like that. Leave it. Why not? Here you go. Very generic path from A to C. I'm going to get this guy thicker to look nicer. And on the top of that, now I don't need that that anymore. Right? I don't need this guy anymore. I don't need that. You know, pass. Now I'm going to just call it a pass, generic pass. Generic pass. And I gotta put an arrow there as well. This one here. My arrow is so small. Let's make it larger. Yeah. Right. And like that. You see an arrow here, right? Because the potential energy doesn't depend on the path. So all we have to do is to state that the work done by this conservative force is going to be the final potential energy minus the final potential energy plus the initial potential energy. Okay. Okay, so here we go. Easiest one. Work done by mg is going to be minus final potential energy minus initial potential energy. Oh, gotta put the E there. Work done by mg from A to C, okay? From A to C. Like that. And now that's going to be mgy, okay, minus mg y naught. And let's go here. Go. The negative sign goes here. The negative sign combines the negative sign. Okay, and we get something like that. That's the work done. I'm gonna put this right one in parentheses. $943, we're almost there. Let's see here. Yeah, this one must be a minus here, right? And then the minus sign is gonna cancel. Right in here. And that's what we get for the mg. The change in potential energy is going to be mg delta y. Okay. So the situation is like that. You know, there is a very nice intuitive interpretation for that. Okay. There's a very nice intuitive interpretation for that. Let me stop sharing this screen. So you can have an intuitive idea that's easier to picture than all those mathematical equations, okay? And the situation is like that. Here you go. I have this object right in here. This object at this position, it has one potential energy. I gotta use another one. Here. Oh my goodness. Bear with me, folks. My battery is like a diet. Oh, okay, good. I'm gonna get something else. Here you go. Here you go. My cell phone, better. Here you go. This object has, my cell phone has a given potential energy at this height. I raise my cell phone against the force of gravity. I am pumping potential, I pump potential energy into the object because I raise it, it gains some potential energy. Okay, and potential energy is what? Is energy that you can use to do some work. Okay, so the higher an object is, you go, the higher an object is, the higher its potential energy becomes. Okay? So that's one example of potential energy. The next easiest one is the elastic force, okay? The next easiest one to calculate, you know, next easiest one means the next easiest one to calculate. The next easiest one to calculate is the elastic energy. Okay? And the elastic energy, you remember, is half the conservative force is half kx squared. Is that force that changes, right, with position. And in the case of the elastic force, now here we go, I'm gonna put, I'm not gonna do the math here, but you already know that the work done by a force that changes with position is going to be the area below that line, right? Remember that? We covered that. So in the case of this elastic potential energy, since it's the area of a triangle, okay, you're going to get something like that, you know, half kx final position square minus half kx initial position square. That's what we have for elastic potential energy. The above, I'm gonna write that down here, is obtained, right? When you calculate the area below the curve of the elastic force versus the position. Okay. And from A to B to C means, you know, here is going to be X position at point C, and here is going to be X position. It's better if you look at this point, this way, okay? At point A, okay? You're going from A to C. A is the initial position, C is the final position. Here is the same thing, okay? Here's the same thing. Is the Y position at point C and the Y position at point A, okay? But then we simplify the notation. The Y position at point C is the final position that we usually denote by Y without a subscript, and the initial position we denote by the symbol not, okay? So it should be right in here. Okay, that's another notation. So the other one, the third one that you have to know, okay, three types of potential energy that you have to know. All those three, remember all those three conservative forces that I mentioned to you before. The next easiest one, and next easiest one, I mean, next is easier one to calculate, okay? The next easiest one to calculate is that of a elastic energy. Oh, wait a minute. It's not like that. It's minus kx, okay? Sorry, here you go. It's minus kx. That's the force, the conservative force. I was mixing up with the potential energy, the equation for the potential energy. Here you go. Let me. Okay. And finally, here is going to be next. Continue numbering. Let's see. No, he didn't do it. I'm going to put set numbering value, better. Good. Oh my goodness, he's not cooperating. There are some tricks here with Word documents, especially when you're numbering everything. Go. The next easiest one to calculate is the elastic, is the potential energy of the elastic force. Better like that. Is the potential energy of the elastic force. Okay. We calculate the area below the curve of the elastic force, below the curve of the elastic force graph versus position graph. Okay. Height is kx, right? And is a triangle. Height is kx. Oh, I need to share the screen again with you. Here you go. I am height is kx, base is x, but because you have a triangle, the area is going to be your kx times x has to be multiplied by half. The next one is more difficult to calculate mathematically. We need calculus. Oh gosh, here you go. Yeah, okay, good. And let's set here number 3. Set numbering value. Let's see if he does it. Okay, now he did it. The next one is more difficult to calculate, and require calculus. The next one, universal gravitational force, is more difficult to calculate and requires calculus. Okay, and don't forget that you have to memorize. Okay, this one you have to memorize. This one you have to memorize. Universal gravitational, UG stands for universal gravitation. Universal gravitational force. Okay, I'm gonna put it UGF is going to be minus big G. No, big G. Big G, big M, small m divided by R. Okay. I'm not gonna go through the derivation of that because it requires calculus. So just memorize that and remember, right, that the force due to gravitational attraction, is given by those two equations. Are very similar, by the way. The force and the potential energy is very similar. We have R squared here. We have big G here. We have big G here. Big M and small m. R is okay. Big M and small m. But whereas the force is R squared, the potential energy is going to be, given by minus. We go like that. And then there is more. Okay, there is more. This thing here can be simplified. Those two here can be simplified. Okay. We usually simplify the above by setting the potential energy to 0 at some arbitrary position. In general, it's going to be at the ground. In general, it will be at the ground. At the ground, okay? At the ground. And instead of talking about work of mg from one point to another, or the difference in potential energy, right? Instead of saying something like that, we just go ahead and simplify the whole thing by stating that the potential energy is given by mgy, whereas at y equal to 0, the potential energy is going to be 0. And we do the same thing for the elastic force. We usually simplify the above by setting the potential energy equal to 0 at the point of equilibrium of the spring. Okay? At the point of equilibrium of the spring is not making any force, it's not applying any force whatsoever to the object or the tip, right? And consequently, the potential energy, we say that the potential energy is equal to 0. And now the potential energy for this case, elastic energy becomes just half kx squared, where x is the distance from equilibrium. Is the not the distance, the position. So because this position can be negative, okay, from equilibrium of the spring. Okay. Notice the following. Notice the following. Here we're gonna put. I'm gonna put mg. Okay. Potential energy due to mg, to the weight. Potential. Here I'm gonna put potential energy of universal gravitational force, like that. Notice the following. 1. PE due to mg is equal to 0 at y equal to 0. Usually at the Earth's surface. Okay. And here you go. Very soon we're gonna go to our break. Okay. PE elastic is equal to 0 at x equal to 0. Which is the position, which is always, here you go, always the position of equilibrium of the spring. Okay, and the third one also notes that for universal gravitational force or universal gravitational law is equal to 0 at r, oops, lowercase r. And I'm going to do the following. Here you go. At when this term is going to be 0? This term is going to be 0 whenever r goes to infinity. Let's see, where is infinity here? Right in here. Okay. Y is equal to 0 is an arbitrary position, okay? But it's usually at the Earth's surface. Here is always at the position of equilibrium of the spring. And here it's always at a distance that is infinitely distant from the object. When r is equal to infinity, this term here becomes 0. And what I want to do now, any questions before we move forward? 10:01 right now. I want to take attendance.
Professor, I have a question.
Go ahead.
Did other students drop the class after the exam too?
I didn't understand. What did you ask?
Did other students drop the class after the exam too?
The other students, you're asking if the other students dropped after the exam too? Is that what you asked? I do not know. I do not know. I didn't check the roster. Okay, but I will check. Okay, Sky, are you there?
I'm here.
All right, thank you. Tessa, are you there? Tessa is not here. Destiny, are you there? I don't see Destiny. Gael Garcia, you're not there. Ridwan, are you there? Hello, Ridwan. Okay, I'm gonna put a star. Okay, Ashley, are you there?
Professor, I'm here. I was saying it in text.
Oh, okay. So let's see here. Someone left some messages here. Okay, Ridwan is here. Ashley is here. Okay, good. Thank you. Ashley Norberto. Are you there? Okay, Annabelle. I don't see Annabelle here. Vanessa, are you there?
Here.
Thank you. Catherine?
I'm here.
Okay, Camden is here.
Yes,
Victoria Preciado. I don't see Victoria here. And Alexis. I don't see Alexis here. Marco Sanchez. Okay, good. 8. Okay, so it's 10:03. Let's take a 10. Let's see here. Okay. Yeah, don't forget in the second exam, I still have to adjust the grade for that question, right? That was not, that we were having problems. I believe it was question number 8. I'm going to adjust the grade for that. I believe it was the worst 3.5 points, something like that. And also, just to let you know, I didn't write that in my syllabus, but I usually curve the grades at the end of the semester. Okay. So if you're feeling a little bit, I chose 12. You told us to shop. To skip. Just 12. Okay. I thought it was 8. Yeah, but okay, it's just 12. Yeah, it's just 12. I'm gonna think what I'm gonna do that. I think I'm gonna give the points for that question. And if you're feeling a little bit uncomfortable about your grade, I usually curve the grade, okay, at the end of the semester. So let's take our break now. Break 10:15 to 10:15 a.m. to 10:30 a.m. And I see you in 15 minutes. See you then. Stop sharing. Recording. What we're going to do now? Let me put that 05 until 10:20. Must have been 10:10. 25. Okay, so examples. Examples of the use of conservation of energy. Okay. Okay. There is a different way of solving problems. There's a problem like let me see if I can find it, the guy here. Okay, I'm gonna enunciate the problem and then I will make a drawing for it, okay? Here you go. Using conservation, you are at the top of a building of height h. You release a small stone. Release, remember? Release. I don't propel it, I release. Release means V naught equal to 0. You release a small stone from the top of this building. What is the final velocity of the stone just before impacting the ground? Okay, just before impacting the ground. Example. Use arguments of conservation of energy. Conservation of energy. You can do that. You could do that using kinematics, right? Like we did before, but you can, but in this case, I want you to do that using conservation of energy, okay? Solution is gonna be like that. But first, before we go to the solution, let's illustrate the situation, okay? And the way I'm going to illustrate the situation, I'm going to use this one right in here. Okay, I'm gonna draw my building right here. Here's my little pebble or stone. And don't forget, ignore air resistance, right? Ignore air resistance. Height of the building is H. I don't need that here. Nothing like that. Here you go. I don't need that. I don't need that. That's the illustration you gotta do. Initial velocity here is going to be 0. P naught equal to 0. Subscript. Like that, you go. Just before impacting, this stone is going to have a velocity that we want to calculate using arguments of conservation of energy. Find the final velocity. Oops. Oops. Okay, that's the situation. Here you go. Refer to the work kinetic energy theorem. Okay, refer to the work kinetic energy theorem. Going back to our relationship that we saw before, the full work kinetic energy theorem is this one right in here. And work of the conservative force plus the work of the non-conservative forces is going to be equal to the difference in kinetic energy. I already told you that since the rock is released, right? V naught is equal to 0, which implies that Ke naught is equal to 0 as well. Like that. So the first thing, the first simplification that we get is this one right in here. We are neglecting air friction, which is a non-conservative force. Okay, so the second term on the right side is going to be 0 as well. Okay. Don't forget that my kinetic energy can be rewritten as half. Don't forget this kinetic energy is the final kinetic energy, right? So it's going to be the final velocity. That's the guy that we want to find out. That's the term that, that we want to find out. Okay, the only conservative force acting in the stone is mg. Okay, and let's not forget that this term on the left side is in reality, right, minus the change in potential energy, minus the change in potential energy, which, by the way, is final potential energy minus initial potential energy. Like that. And now, the final potential energy is going to be mgh. mgh. One more thing that I didn't do. Oh yeah, I already did. I set the ground floor at the origin of my y-axis. Okay, so they need let's see. No, sorry, it's all the way around. The final potential energy. Here you go. The final potential energy is going to be mg y, right? And the initial potential energy is going to be mg y naught. Okay, like that. And don't forget, it's going to be the final. Let's continue with that. Here you go. Negative here, positive here. Okay. And then we have this term. Okay, so you know that the initial position is going to be h, right? And the final position is going to be 0. I'm going to put 0 here, just to emphasize it. The relationship is this one right in here. Then what we are left with is going to be something like that. Oh, by the way, m cancels out. See that? So it doesn't depend on the mass of the particle, even though I didn't give you the mass. Notice that I didn't mention what was the value of the mass. 2gh, and I can have the square root right here. That's my final velocity. You'll get the same result if you were to use the kinematics equations, the equation of kinematics. I'm going to come up with another example.
But I have a question. Isn't this
Yeah.
like a trajectory formula as well? No?
What's the question?
Trajectory formula is kind of similar to this one, right?
Trajectory. Well, this trajectory is simple, right? This trajectory is a straight line.
Yeah.
Okay, this trajectory is simple. So, we do all that convoluted trajectory to show to you that all those ideas, right, is applied to the very generic situations. That's why. Okay.
Oh, okay.
Okay, so let's move a little bit up here, just before impacting. Okay. And now I want to do a different one. Let's see this one here. Let's see. Yeah, let's get this one. We're going to do another problem, another example. It's going to be like that. Okay. And example using elastic force. Example 2. Example 2. Oops. Example 2. elastic force. Yeah, let's see. I want to do another one. Let's see if I have a drawing here. Yeah, I want to do this one instead. It's easier to visualize this one than the other one. Okay, so here you go. You compress and you attach a spring to a mass. You compress the spring, and the mass is not attached to the spring. Okay, it's just resting here. The mass is not attached to the spring. It's going to be something like that. Okay, it's like a plate. The mass is resting over this plate that attached to the spring. And I'm going to put here initial position X. A distance. Yeah. X naught. Let's put it this way. Position X naught. Oh, sometimes those things doesn't work as advertised. Let's see. What about now? Better, right? Okay. Okay, so the situation is like that. A metal plate is attached to a spring of constant K. Okay, a mass, an object, okay, an object of mass M is compressed against this plate and displaces the spring by an amount X naught. You release the mass from rest. Okay, what is the velocity of the mass at the position of equilibrium when the mass loses contact with the plate? Okay, ignore, ignore friction, neglect friction, and other non-conservative forces. Okay. So the situation is like that. You're gonna play the movie. All right, let's see if I have it here. No, I don't want this one. I want this one here. Okay, at this point in time here, the force is 0, but then I have to put that plate there, right? Let me but a little bit longer than that. The plate that is attached to the spring, but is just touching the mass. At this point in time, the force that the spring is applying to the mass is 0. Okay, and I can also draw a velocity vector here, like that. Yeah, it's the math that got out a little bit off. Ay, 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 ay. Good, like that. Okay. What is this velocity? At this point in time, the force is about to change direction, right? It's about to, the force is 0 and it's about to change direction towards the left. So the mass is only resting right here at the plate. So the moment that it reaches here, the mass is going to lose contact with the plate. And it's going to be propelled to the right. It's just like a spring gun on those spring gun toys, right? So a metal plate is attached to a spring, attached to a spring of constant K. An object of mass M is compressed against this plate, compressed with the plate, and it's not attached. Not attached. The metal plate is attached, not the mass. And this displaces the spring by an amount x naught. You release the mass from rest. What's the velocity of the mass at the position of equilibrium when the mass loses contact with the plate? Neglect friction and any other conservative forces. Okay, so we go, we're neglecting any other non-conservative forces. Since you're neglecting non-conservative forces, we have something like that. The only conservative force that's left is going to be the elastic force. Elastic force. We do have the force of gravity, the mg, but the mg, the change in potential energy is 0, so you don't have to account for that. And this elastic force is going to be equal to half k x final square, right? That's going to be my minus half k x naught square. It's going to be like that. And I want to find out what's going to be this one here. Okay, the initial kinetic energy is going to be 0 because the mass is released from rest. So wait a minute. Sorry, it's not like that. Okay, it's more like that. The initial potential energy is going to be that. Okay, that's going to be the initial potential energy. You are applying, you're compressing the spring, and you adding potential energy to the system. Okay, so here we go, and we have this relation right here now, and that's going to be half mv square, the final velocity, half cancels out with half. M goes downstairs. And then we are left with this square root here. The square of x naught becomes x naught. And that's what you get for the final velocity. Yeah, by the way, the best way, let me redo that for you so you understand that better, okay? Don't forget that this elastic potential energy is what? Is minus delta potential energy. Don't forget that, okay? There's always a minus here for the potential energy, right? And the change in potential energy is going to be what? Half k x final square minus half k x naught square. Okay, now it's gonna make more sense. Okay, you have this negative here. This x final is going to be the position of equilibrium. The position of equilibrium is going to be 0, right? And now this negative cancel out this other negative, and you end up with this term right here. That's the step-by-step procedure here. Mathematical procedure, step-by-step mathematical procedure. The key here is the negative. Don't forget, the work done by conservative force is always minus the change in potential energy. And we are going to do another one. Now it's going to be the third potential energy that we universal gravitational law, right? Or force. Universal gravitational force. Okay. A super gun. Super gun is propelling well, you can think in terms of a super gun, or you can also think in terms of this new device that this company developed. I don't know if you folks is following that, okay? Let me see if I remember the name of this device. It's a really neat way of sending objects to low Earth orbit without spending chemical fuels, okay? It's a spin launch. Let's see, spin launch. Yeah, spin launch company. Have you seen that? It's really exciting what those guys are doing, okay? They came out with a completely different way of launching payloads into space that doesn't involve rocket fuel. It involves, let's see here. Oh, yeah? Tossing satellites into orbit with spin launch. Is that possible, right? And the first payloads, I'm going to show that to you. It's not, there are two ways to do that, right? And some time ago, one Canadian guy, they came up with this super gun, which was a super cannon capable of propelling projectiles at very large distances. It's a fascinating story. Okay, this guy ended up working for Saddam Hussein there in Iraq, and the story is described in a movie by HBO. It's the Doomsday Gun. That's one way of doing that, using a big cannon, a super gun, okay? And the other way of doing that is the way that those guys, spin launch is doing. Let's play a movie here so you can have an idea. Good morning, everyone, and welcome. Here you go. Let's take a look here at the facility. Do you see that? This is the gun, right? The barrel of their gun. But then what we have here? We have a centrifuge that's gonna rotate the payload at very high speeds and then bang, propel it at very high altitudes. That's a very unique way that those guys found out of launching payloads into space. And it's very cost effective as well. So let's take a look. I'm gonna lower the volume a little bit here. And here.
Good morning, everyone,
Here you go.
and welcome
Spin Launch is the name of the company. They must have the patents for this device.
to Flight Test 10. Today is a really big milestone for the company. It is the first time that we're
Oh, do you see here the rocket? They are taking the rocket, okay, out of the casing. Okay, here you go. The rocket out of the casing, right? Inside this rocket, we have the payload that they want to launch in orbit. Spin launch, blah, 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 right?
first time that we're flying external.
Oh, here you go. He's loading the rocket into that big centrifuge that you saw.
Payload on our flight vehicle. In fact, we're flying a NASA payload, Cornell University, Outpost Space.
So those guys, obviously, they have a contract with NASA because NASA is always looking for novel ways of launching payloads into orbit and at high altitudes as well.
And Airbus all on board with
The most expensive part of launching something in orbit is to leave the Earth's surface. Okay, that's the most expensive part. If you can lower the cost of propelling something at very high altitudes, you are in the way to lower access to Earth's orbit.
us today.
Here you go. It's a really crazy idea. Okay. When I saw that, I couldn't believe those guys did that. Okay.
We had over 100.
Look here. I wanna move a little bit up right in here.
We had
Okay. So most likely this picture was taken as a drone, right? The barrel that you see here, and that projectile is gonna be spin it. Oh, but it's gonna spin it in this direction actually. It's gonna be spun in this direction. And then you have a device that allows it to leave the centrifuge when it reaches high enough speed. It has a device that opens a little door here that allows it to leave the centrifuge and goes inside this gun, right?
over 150
Here you go.
people here from industry, aerospace, satellites, space, government, Department of Defense, and to be able to
150 people. We're not talking about 500 people. 150 people is the size of a small company. Okay? We're not talking about 500 people. We're not talking about 1,000 people.
share this with the world is so incredibly energizing and exciting, and it's such a proud moment for us and for the team that got us here.
Look at the size of this contraption, right?
Even as I'm trying to explain, somebody chills. This day to me has been amazing on so many different levels. And to be a human and just to arrive today and to see an example of a mega engineered structure that is so different from anything I've ever seen before makes me so happy and hopeful.
We were one of the payload partners for Flight Test 10, and so it proves out that you can use host to off-the-shelf components for launch, and also in
Look the size of the guy compared to this structure, right? It looks like something like 3 meters, 4 meters across. It's a barrel 4 meter diameter, more or less, 4.5 meters maybe.
it's been launched with environment, even though there's high loads.
1,000 miles. 10, 9, 8, 7, 6,
Oh,
5,
wait a minute. You see the countdown, right?
4, 3,
Let's see.
2, 1. There you go.
Whoa! See that? It's crazy.
Obviously, a very impressive sort of capability, very outside the box thinking. And I saw that throughout everybody we talked to here at Spin Launch. They're thinking about non-traditional challenges.
It's been a journey, and today we accomplished our 10th test flight, and it has proven that it is a system that is repeatably reliable.
That's very important. A system repeatedly reliable. Regular rockets today are not reliable. They can blow up almost any time. Okay, just like happened with the space shuttle when it was entering the Earth's atmosphere, and even the Virgin Galactic spaceship one, they had a spaceship two actually, right? They had a terrible accident that killed one of the pilots and disabled the other pilot that was in the spaceship two.
This is not a rocket. And clearly our ability to, in just less than 11 months, perform this many tests and have them all function as planned really is a testament to the nature of the technology.
Okay, so why I'm showing you that? Because this problem is related to something like that. It's not a super gun, but let's say the spin launch, a spin launcher, right? Launcher propels spin launch launcher propels payload.
I have a question, Professor. Are they trying to weaponize the payload, or they're trying to just send these payloads to the out of orbit?
Well, it's possible to weaponize it. Yeah, it's possible. I haven't heard spin launch doing that for weapons, for weapon delivery. I haven't heard. Everything that I have seen about spin launch was to launch those projectiles at very high altitude so they can get into orbit. Okay.
Oh,
But it's possible. Yeah, I'm quite sure it's possible. Just like Saddam Hussein was doing with the super gun from the Canadian guy. Okay, there was this Canadian guy called Gerald Bull, and he used to work for the American government building big guns, and his dream was to use his big guns, his super gun, his super cannon, to propel objects to the moon surface. And he never would be able to get to this point where he would convince the American government to fund him to get to this point, okay? To get a super gun to launch an object into orbit. Okay, and because of that, he started to hang around with the wrong people. Okay, he started to pass secrets from the United States to the other powers. He was arrested. Okay, but that guy ended up weaponizing his super gun. Yeah, I haven't heard that spin launch is doing that, but most likely the military must be talking to them. Yeah, I'm quite sure the military must be talking to them.
Okay.
Okay. A spin launch launcher propels a payload at a very high speed, in the vertical, along the vertical direction. Very high speed V, okay? Along the vertical, very high speed, comma V, along the vertical direction. What is the maximum height? Find the maximum height. Find the maximum height of this projectile using arguments of conservation of energy. Arguments of conservation of energy, right? Spin launcher propels a payload at very high speed V along the vertical direction. Find the maximum height of this projectile can achieve using arguments of conservation of energy. Consider that the height is high enough so you have to use the universal law of gravitation, right? Universal law of gravitation. Neglect friction and other non-conservative forces. When you get friction involved, it becomes far more difficult, the problem, okay? It's like that. Okay, so conservative, non-conservative forces, okay, so here we go. we are neglecting non-conservative forces. The only conservative force is the force of gravity, and you end up having the big G, big M, mass of the satellite, okay, and distance of the satellite. And by the way, this distance R is from the center of the Earth, okay? It's from the center of the Earth. Okay, and we must have a negative here. Okay. And the situation goes like that. Here you go. I gotta come up with a drawing here for you as well. Here's the Earth. Here's the Earth. And 11:05, let's see. No fill, okay. You're going to propel that guy at very high speeds upwards. This is the radius of the Earth. Okay, and this object is gonna reach very high altitudes in such a way that the G here, acceleration of gravity here, is not going to be 10 meters per second square here. That's why you have to use that formula that's more complicated, okay? That's why you have to use that formula that's more complicated. And oh yeah, you have to have a positive here. Don't forget work done by the, right? Has to be minus the change in potential energy. So it has to be minus right in here. I want to find out this value right in here. And I'm asking for the maximum height. Okay. Changing potential energy. Let's see. Final potential. Oh, there is one more term here, right? Final potential energy, like that. Let me show you what it is. That's going to be my initial potential energy right here. Initial potential energy, okay? And that distance that you saw is the distance from the center of the Earth, very important. Okay, and this one here is going to be my final potential energy. Okay, I'm going to put one more piece of information here. The radius of the Earth is big R. Okay, radius of the Earth is big R. The small r is the distance from the center of the Earth. Okay, that's the small r is all about. The distance from the center of the Earth. Here is going to be big R. And what you see here is going to be big R plus H. Like that. The maximum height, right? Is going to be big R plus H. And we want to find H, big R plus H. At this point, at this height, I'm gonna put, oops, no. At this height, the velocity of the projectile is going to be 0. The final kinetic energy, right? And at this height, the initial, right? You're going to have a velocity V, the initial kinetic energy. It's far easier, right? If you go ahead, instead of remembering that equation, it's far easier that if you transform what you see right in here in the equation for conservation of mechanical energy. Final kinetic energy plus final potential energy is equal to initial kinetic energy. That's what this equation reduces to, right? Initial potential energy. Okay? And I want to know the height, the final height of my projectile. The final height of my projectile is implicit right in here into this equation. Okay, the final velocity is going to be 0. Consequently, the final kinetic energy is going to be 0. The initial potential energy is half mv squared. I can put v naught squared if I want. The potential energy at the Earth's surface is going to be minus big G, big M mass of the Earth, mass of the satellite is going to be divided by R, which is the radius of the Earth. Don't forget, this potential energy that you see here, this potential energy here that you see here, this R is the distance from the center of the Earth, okay? 1, 2, 3. Small r is the distance from the center of the Earth. Okay. And the final potential energy is going to be minus big G, big M, small m, divided by lowercase r. But don't forget, this lowercase r is going to be given by the radius of the Earth plus the altitude of the satellite, the altitude of the payload. Okay? Find the maximum height this projectile can achieve using arguments of conservation of energy. And now the equation that you have is this one right here, and I want to find out this guy. I'm going to highlight it. Okay, how do we do that? It's gonna be a little bit, Oh, the first thing that we can do is to cancel, Okay, the radius of the Earth is R and its mass is big M, okay? So we know the radius of the Earth and the mass of the Earth. This height is not gonna be a function of the mass of the satellite. So we know almost everything here. The only thing that we know is this one, right? Let's see how we're gonna solve it, right? So we have to put everything, let's see. I'm gonna pass negative to the other side. Okay, I'm going to put this thing between parentheses. We're gonna have a big G, big M, like that. And then we have to put this term here under the same denominator. If we do that, we gotta put this one also under the same denominator. Okay, and 2R is gonna go outside. Minus R. Oh, minus R is already there. And 2R already put that 2M. That's the equation we want to solve. Okay, and finally, you can see it a little bit more complicated than the other. Pass to the other side. Right? And finally, that's what we end up getting, minus R. That's the maximum height that the satellite achieves. The payload achieves. Then we can plug in some numbers in there, okay? A very good number for V should be around 7 kilometers per second, which is the orbital speed, not necessarily high speed to put it in orbit because it's being shot upwards. But if you make V, you know, calculate, I want you to do that at home, okay? Homework on your own, okay? Homework homework. I'm not going to correct that. I just want you to have a feeling of what it takes, okay? Calculate H for the find H for the following initial velocities. 7 kilometers per second, 9 kilometers per second, and 11 kilometers per second. Okay, so 11:15 right now, 11:16. So I did 3 different problems. Okay, one example for each one of those conservative forces. And then there are also, problems that involve a mixture of conservative and non-conservative forces, okay? Non-conservative forces. You might want to do that as well at home on your own, okay? And let's go back here to our spin launch, this one here. Okay, the only thing that's left now is we did, let's go back to my notes. I have here a list of the chapters from the book so far. Okay. Work done by a constant force, we did that. Work done by kinetic energy, kinetic energy theorem, we did that. Gravitational potential energy, we did that. Conservation of mechanical energy, that's just a consequence of the work kinetic energy theorem, okay? Conservation of mechanical energy is just a consequence of the, is a special, let's see, is a special case of the work kinetic energy theorem. Work kinetic energy theorem. non-conservative forces and the work kinetic energy theorem, non-conservative forces, and let's take a look at these other forms of energy. Okay, the book, other forms of energy and conservation of energy. Here you go. Sometimes it doesn't go there. What a shame. 6.8, 6.7. We didn't do 6.7 yet. Other forms of energy and conservation of energy. Okay, we're gonna kind of skip this one. Yeah, we're gonna skip this one. Okay, so the only thing that's left is power. Skip. That's the only thing that's left here. And it's 11:19. I wanna go for another break. Break 11:22. Let's take a shorter break this time. 11:30 a.m. Okay, 10 minutes only. So you can finish this chapter and hopefully start the other one. Any questions? Okay, I see you in 10 minutes. Okay, I'm back here. Last thing is power. Last thing is power, okay? And there's a reason why we define power. There's a very good reason why we define this concept of power. Okay, think about, you know, this idea of energy is closely related to the amount of work that a machine can make. It's not just, it's not just it's not just related to rockets or other things, okay? But it's also related to machines like a crane, for instance, okay? Suppose, I want you to think about it. Suppose that you're in the market to buy a crane, something that can lift a heavy load, a very heavy load, 1,000 kilograms load to a height of 10 meters, right? And you ask the salesman, and he tells you that there is a specific crane that costs $10,000. It's hypothetical, okay? Then you go to another store and you find out. And then you go to another store. You don't buy that crane yet. You go to another store and you find out there is a much cheaper crane out there. It's half of the price. It sells for $5,000. And don't forget, when you tell the salesman that you want to raise a load, 1,000 kilograms load, 1,000 kilograms load to a height of 10 meters, basically you are telling the salesman that you want a crane that can do a work of 10,000 joules. Okay, 10,000 joules. That's what you're asking the salesman. I want a crane that can do work on the amount of 10,000 joules. Okay, so this store tells you that the crane could cost $10,000. You go to a second store, and this other salesman tells you that he's selling something that can raise the same load to the same height for half the price. Okay, is there anything wrong here? You gotta start thinking about that. Are you getting the right crane to do the same amount of work, right? So the second crane is cheaper than the other one, but what's the difference? Why is half cheap? Okay, the difference, has to do the difference between these two cranes has to do with something that we call power. Okay? Both cranes can perform the same job of lifting the same load 10 meters high. However, at this point, you have to stop and ask the salesman, the two salesmen, right? What is the power of each crane? In other words, what's the power of each crane? In other words, how long each crane takes to do the same amount of work. That's what power is all about, okay? Maybe the second crane is cheaper because it raises the same amount of load in half the time, twice the time as the other one, at a much slower pace, or maybe even 3 times as much time. Okay, if the first crane takes like 5 minutes to raise 1,000 kilogram load to 10 meters, maybe the second crane is cheaper because, 15 minutes, right? 15 minutes. Maybe the second crane is cheaper because it takes 1 hour to relieve the same load. Okay, that's what power is all about. Power is how fast you can perform a given amount of work. Okay, that's what power is all about. So let's say the first crane perform the first job in 10 minutes, but, and here you go, in a big but here, but the second crane, because it is cheaper, most likely perform the same amount of work in a much longer time, let's say 20 or 30 minutes. Okay, that's why the second crane is cheaper, because it's less powerful than the other one. Okay, that's why the second crane is cheaper. Because it is less powerful than the first one. Okay. And how do we define power? Okay. Power is defined in the following way. Power is defined as the amount of work divided by the amount of time. Okay. It's like a speed, right? A speed of amount of energy. And this idea of power shows up so frequently that it has a special unit. Okay, but first let's take a look at the unit of power. Here you go. The unit of power is going to be the unit of work divided by the unit of time, and it is joules per second. This unit shows up so consistently in physics that we give a name, we call it watts, and abbreviate by the letter W. Okay, do not mix up, W for watts, right? with the abbreviation, right? Abbreviation for weight, with the abbreviations, right? For weight, W equal to mg, and work, right? We're using the same letter for different things. But there are other powers. There are other units of power. Horsepower, for instance, one of them. One of them. Okay. There is another interesting equation here that we can derive for the power. Okay. Don't forget, amount of work is what? Is force times delta R. Gosh. Go. And if it's one-dimensional motion, right, it's going to be delta X. And look what we get. We get, we can have the same equation written in a different way. Delta X over delta T is V. And we end up with the force times V. Okay.
Professor, I have a question.
Yeah.
How come there's like same equations between?
Are you talking about the letters?
Yeah, the letters.
Yeah, that's a problem in physics, right? We run out of letters and we start recycling them for different things. It happens fairly frequently, so you have to be careful about that. Okay, it's not ideal. It's not ideal, but it happens. It's not ideal, but it happens. Okay. Good. Okay, so let's do an example. Let's see here. Okay, so going back to the cranes you're buying. You were buying, right? The first crane example. The first crane that's the same amount of work in 10 seconds. Let's see now, 10 seconds. Whereas, let's see. The first crane lifts, let's put it here, lifts 1,000 kilograms to a height of 10 meters in 10 seconds. Whereas the second one lifts the same load in 40 seconds. Calculate the power of both, right? Solution. Okay, so first one, amount of work, that's going to be 10,000 joules, 1, 2, 3 joules divided by 10 seconds. Right, then you end up with 1,000 watts. The second one, 10,000 joules, but now it's going to be 40 seconds. And you're going to end up having 1,000 divided by 4, 250 watts. It's half the price, but it has 4 times less the power. Okay, and that's what we have for this chapter. It's 11:45 now. And what I want to do this time, don't forget, we are doing other forms of energy. Yeah, we did power. Yeah, we're skipping only this one here. What I want to do now is start with chapter 7. Okay. Okay, that's linear momentum. How we call it? Let's see what your book calls it. Momentum. We are not gonna do impulse momentum theorem, okay? Let's take a look at the chapters, the sections of this chapter, and then I tell you exactly what we're gonna look at, what we're gonna cover and what we're not gonna cover. Here you go. 7.1 impulse. The impulse momentum theorem. Skip. Then principle of conservation. The principle of conservation of linear momentum. Yeah, we're gonna do that. Collisions in one dimension. Collisions in 2 dimensions. Collision in 2 dimensions. Yeah, and we have the last one. Last one is important, center of mass. Yeah, we're not gonna do, I don't think we're gonna have time to do center of mass, but we're gonna do at least those 3, okay? Skip. Okay, let's see where this idea of momentum shows up. Okay, the idea of momentum is closely related to Newton's first and third laws of motion. Okay, I want you to remember the following. You know, recall that the net force, oh, let's do it differently here. Okay, the net force is m times a. Okay, the momentum is very close to that, and there is more. I'm gonna go a next step here. It's also can be written as delta v over delta t. Okay. Okay, the idea of momentum or linear momentum, right? I call it linear momentum because there is something called angular momentum as well. The formula, okay, not the idea, the formula of angular momentum, of linear momentum is very similar. It's quite similar, not very similar, it's quite similar to the above one. The difference being that instead of m times a, We call it linear momentum P. Is a vector, by the way. Instead of m times a, it's going to be m times v. See the v right in here? The difference is that we have delta v, and I also have delta t there. Okay, and there is a reason why we define that. There's a reason. There is a very good reason. Why we define this quantity. Okay. Think about the first law of physics. Think about the first law, first Newton's law. Okay. In the case of the first, in the case of this law, okay, the equation for the net force becomes what? First law, net force equal to 0, right? That's what first Newton's law says. If the net force is equal to 0, the object is going to be moving either with constant velocity or it's going to be at rest. But there is more to it. If we apply second Newton's law to this specific circumstance, what we are going to have? We are going to have the following, folks. Take a look here. We're going to have final velocity minus initial velocity here, okay? And there's more. There is more. If we pass the delta t to the other side, you go, okay? If you pass the delta t to the other side, we're gonna have something that's fairly similar to what we saw for the linear momentum. We are going to have the following situation. We are going to have that the final momentum is going to be equal to the initial momentum. Do you see that happening here? That's why it's so important, linear momentum. And I'm going to rewrite that. Here you go. Final momentum is going to be equal to the initial momentum. Okay, consequently, for the case in which the net force is 0, we do have a conservation of momentum. Not just conservation of energy, but conservation of momentum. Initial moment, in other words, initial momentum is equal to final momentum. Okay? That's why we define this quantity of linear momentum, because there are many situations in physics in which many important situations in physics, not just many situations, but many important situations in physics, in which the net force applied to a system is going to be 0. Okay? And then we're going to start, I'm going to start with the simplest of all examples that I'm going to see out there. Let's go back here to my drawings here. Oh yeah, here you go. Okay, no friction. We have this block resting over the surface, frictionless surface, and it's moving with constant velocity. Since there is no friction, time t equal to 0, since there is no friction. Later on, at time equal to t1, The object's going to be moving under with the same velocity. mv here is going to be equal to mv here. That's the most obvious situation that you're going to see conservation of momentum. But then there are some situations that are not so obvious. That's why we study linear momentum, okay? But like I said, this one is the most obvious situation, okay? No friction, momentum is conserved, momentum here is equal to momentum here is equal to momentum here, and momentum here is equal to momentum here as well, okay? Just one body, moving with constant velocity, momentum is conserved because the net force applied to this object is going to be 0. Now, we are going to start studying a slightly different system, okay? What you see right in here, the single object moving, is what we usually call it a system, our system, okay? And then we can come up with a different type of system like this one here. Instead of just one object, two. It's still a frictionless surface, okay? Still a frictionless surface. And I put this box around here to emphasize the fact that my system is this first mass, okay? This first mass is moving towards the second mass over a frictionless surface. From here to here, the momentum of the first mass was conserved. But then something happens. The first mass comes in contact with the second mass. The net force on the first mass is no longer 0, and then something is going to change. What's going to change is going to be the momentum of the object is going to change, okay? Because a force acted on the first object. Similarly, we can do the same type of we can tell the same type of story here for the second mass, okay? And now I'm just going to draw the box around this guy. Here's my system. Net force applied to this object is 0 because it is at rest, okay? And then the second mass is approaching the first mass is approaching the second mass. It didn't exert a force on the second mass yet. So momentum on the second mass at this instant of time is conserved from here to here. The problem arises when the first mass, funny, isn't that? Let's see if I can get that. It has to be invisible. No outline. No, this one here. No fill. Okay, here you go. You got it. The moment that the first mass contacts the other one, the momentum of the second mass is going to change. And depending on the type of collision that we have, all those two masses are going to move in tandem. Okay, and this type of collision, there's a name for this type of collision. It's called inelastic collision. 2 more minutes to go. This is just a brief introduction of linear momentum and what I want to do. Yeah, any questions about that? Okay, I want to stop here, and next time I'm going to elaborate a little bit more on what I did here. Okay, first, like I said, look what I did. First, I start with a single, just try to summarize everything in those 2 minutes, right? I introduced you to the idea of a single object moving with constant velocity. Okay, this single object is my system. This object here, moment for this case of this object, momentum is conserved because the net force applied to the object is 0. And then I introduce you to another situation with 2 objects. One object approaching the second, the first object approaching the second one. Once the first object feels a force of the other object because of the collision, its momentum ends up changing, right? The same thing must apply to the second object. The second object that was initially at rest when it collides with the first object, it must start moving. Consequently, the second object momentum has changed as well. Okay? So what I want you to start thinking is, what if I consider my system not just a single of the two objects, but I consider my system all the two objects, an object that's changing its size. Okay, here's my system. Okay, first mass moving towards the second one. See that it's approaching. They undergo a collision. Okay, both masses are considered my system, and then they are going to end up moving. Are we going to have conservation of linear momentum under this circumstance? If I just by choosing my system appropriately, I want you to think about that, and we're going to continue this story next time. Okay, on Wednesday. Any questions? Okay, so I see you on Wednesday, and I also have office hours until 1 o'clock if you wanna hang around. Okay.
Professor,
Yeah.
I have a question. I have some questions about lab 4.
Yeah.
So
Okay.
I was wondering that for the sigma
Yeah.
units, do I need to use meter?
Yeah, you gotta do dimensional analysis, right? Did you do
Yeah.
dimensional analysis for sigma?
No, I am trying to figure it out the units, but I don't know what to calculate from here. Like,
Sigma?
yeah, from lab 4, just in general, like
Hmm.
I'm trying to figure it out, like what we need to do. Like, do we need to find standard deviation from the table 4-2
Okay.
or
So let's go back here in lab 4, right? You take a
Mhm.
note, look at the notes for lab 4.
I think I have the manual to read.
Lab 4, let's see here. Lab 4. But what's your question? Let me get your group number 3, right?
So my question was, I don't know, the sigma units, delta units,
Okay.
and the x prime radius average plus sigma units. All
Okay, so
these
let's go one by one here. The first question is, what
sigma
are
units.
the units for
Yeah.
the standard deviation, right?
Yeah.
Okay, let's start with this one first, the standard deviation.
Okay.
Okay, and what's the other question?
And I don't know what to calculate with table 2, 4.2, 4.-2.
Okay, and what to do with table 4-2?
Yes.
Okay, so your group number 3. Let's go there to your group. Download for what? Group 3. Four dash two. 4-2 is this one here.
Yes.
Okay.
And there's another one. If you
Okay.
scroll
Up or down?
up. If you scroll up, there should be one more. Yeah, 4-2.
Okay, this one is not 4.2, it's just 4.4. Let me change it.
Oh, okay. So it was 4.4.
Yeah, this was supposed to be 4.4. Okay, here it's 4.2. Yeah. So what's the question?
Yeah, these two values. I don't know what to do with these two values. Do we need to like find standard deviation with
No, no, you don't
okay.
find a standard deviation. All you gotta do is to display the right number of significant figures here.
Okay.
Okay, all you have to do is display the right number of significant figures.
Okay.
Okay.
How about the 4-5 units? Do we need to use like meter, percentage, meter?
Well, you gotta, yeah, you're asking me to tell you the final answer of that. That's what you're asking me. Okay.
Yeah, I
How
mean
did
that's
you-
what I wrote.
yeah,
like-
but why did you put meter here?
Oh, I didn't put meters on. Oh, but sigma.
Yeah, why did you
Because
put,
that
you
I
put
thought
meter for sigma?
Yeah, yes, I
Okay, why
did.
did you put meter for sigma?
Because I thought sigma is the sum of the total like amount. So
Well, did you do dimensional analysis? Did you do dimensional analysis?
not yet.
Yeah, you gotta do dimensional analysis, okay? From what you're telling me, it looks like you're guessing. You're guessing the unit of sigma, right?
Mhm.
So you gotta look at the equation for sigma. Okay, so here you go. When was lab 4? Lab 4 was lab 4. Lab 1, 2. Okay, lab 4 was 25th of October, right? Okay, right in here. Lab 4. Okay, I gave you the equation for sigma. That's the equation for sigma. Right?
Mhm.
That's the equation for sigma. Okay. And going back to your, what is x? What is x?
Distance.
Distance? Okay, so it's sigma of what? Let's see, let's take a look. It's sigma
Mhm.
of the range. See that?
Right.
Yeah, that's what it is. Okay. And if you do the formula correctly, right, it's going to be something like that. Here you go. X prime I
Mhm.
minus x prime average squared. Okay, so it's going to be each one of those. You take the average of all those things.
Wait,
you get
hold on.
this value, subtract from the average, square it. Right? That's how you do it.
So I need to get average for 4.4. I mean 4-4 average.
That's right. That's what the sigma is doing for you. You don't need to take, you don't need to calculate it because the spreadsheet is already doing that for you. Okay.
Okay.
Okay. You don't need but let's see here. This one like that. I don't like that. Let's see. Okay, so is this one minus the average is squared plus this one minus the average is squared. Do you understand what we're doing here? This one minus the average is square. Okay. What are the units of each of those terms? What is the unit of each of those terms?
Meter, square meter.
Meter to the square, right?
Meter to the
You're
square.
summing meter square. Yeah, because you're squaring, right? This one is meter. This one is meter. You're squaring the meter. So this guy here is going to be meter square, right?
Wait, which one? Yeah, but this is the X range average, right?
Yeah, X.
Okay.
That's right. And then what else do we have to do is this formula? You still have to take the square root, right?
Mm-hmm.
When you take the square root of meter square, what do you get?
Meter.
Okay, that's how you find the unit of sigma.
Oh, okay.
by doing what we did here was dimensional analysis. You have to look at the equation
Mhm.
and determine the unit from the equation itself. Okay?
Okay. So the range should be just meter as well, right?
Yeah, the range is just meter. It's the distance from the point of launch to the point of impact in the floor.
Okay.
Okay, so we had that projectile, right? Here you go, projectile. Here you go. This one here.
Yeah, I
Okay.
remember.
Okay. That's the distance. That's the range. Right? That
Mhm.
we're measuring. So yeah, it's meter
Okay.
from the point of launch to the point of impact. Okay,
Okay.
that's it.
Yep, that's it.
Okay,
All right. Thank you so much, Professor. Have a good one.
welcome. Deixa eu parar aqui.